Welcome to the chapter Heat. This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to describe temperature and heat, explain the concept of thermal equilibrium, discuss about kinetic energy, explain the concept of specific heat, list the applications of specific heat capacity, state the principal methods of mixtures, explain the processes of evaporation and condensation, define humidity, fog and dew, differentiate boiling and melting of substances. Introduction. Click each tab to know more. In lower classes, we learned that heat is a form of energy in transit, flowing from a body at higher temperature to a body at lower temperature. The concept of hotness and coldness using glasses filled with cold, lukewarm and hot water. We also learned that hotness and coldness are relative terms. Heat is a form of energy. Are the terms temperature and heat technically the same? To answer this question, let us do some activities. Let us know about hot and cold objects. In our daily life, we see that some objects are cold like ice and some objects are hot like tea. We also know that some objects are hotter than others while some are colder than others. Commonly, the degree of hotness or coldness of an object can be estimated by using our sense of touch. The hotness or coldness is expressed in terms of temperature. But estimating temperature with our hands can sometimes mislead or confuse us. Let us perform an activity for relationship between temperature and heat. Take a piece of metal and a piece of wood. Place them in a fridge or in an ice box. Take them out after 15 minutes. Now touch them to feel their coldness. Heat transfers from the fingers to the wood and metal pieces. Remove the fingers from the substances and the feeling of coldness ceases. The feeling of hotness or coldness involves transfer of heat from the substances to the body. Here, the metal piece is colder than the wooden piece. It is because the degree of coldness of the metal piece is greater than that of the wooden piece. The term, the degree of hotness or coldness, is defined as temperature. Finally, in terms of temperature, the metal piece is at a lower temperature as compared to the wooden piece when both of them are taken out of the icebox or fridge. Thermal equilibrium, heat and temperature. Transfer of heat takes place when two bodies, one hotter and other colder, come in thermal contact with each other. This process continues till both the bodies have the same degree of hotness or coldness. At this point, we say that the bodies are in thermal equilibrium state. In the state of thermal equilibrium, a body neither receives nor emits heat energy. Example 1. When no transfer of heat takes place between you and the surrounding atmosphere, your body is said to be in thermal equilibrium state with the surrounding atmosphere. Example 2. Similarly, a furniture in a room exists in a thermal equilibrium with the air in the room. Here the air and the furniture in the room are in same temperature. Here, we are going to discuss heat. Generally, when we stand near fire, the heat of fire enters into our body, we feel hot. In the same way, when we hold the ice piece in our hand, the heat is transferred from our body to the piece of ice and we feel cold. Hence, we can conclude that heat is a form of energy in transit. It is always transferred from an object at a higher temperature to an object at a lower temperature. Definition: heat is a form of energy which makes an object appear hot or cold. Take 2 empty cups or vessels or mugs. Fill them with hot and cold water respectively. Now take a laboratory thermometer. Observe the initial level of mercury in the thermometer. Note down the reading in your notebook. Place the thermometer in hot water. Observe the change in the mercury level. Note down the readings in your notebook. Now keep the thermometer in cold water. Observe the change in the mercury level. Note down the readings in your book. We observe that mercury level rises in thermometer when kept in hot water. This implies that heat was transferred from hotter body, hot water, to colder body, mercury in thermometer. Similarly, in the case of cold water, we observe that mercury level comes down from its previous level. The reason is that here the transfer of heat takes place from mercury, hotter body, to water, colder body. From the above activity, we learned that heat is a form of energy in transit. It always transferred from a body with higher temperature to a body with a lower temperature. The steadiness of the mercury column of the thermometer indicates that the flow of heat between the thermometer liquid mercury and water has stopped. That is, thermal equilibrium state has been attained by the water and thermometer liquid mercury. The reading of thermometer indicates the temperature at which the thermal equilibrium state is attained. Thus, temperature is a measure of thermal equilibrium. Thermal equilibrium with 3 bodies. Now, let us learn about the thermal equilibrium with 3 bodies. Consider 2 different systems A and C in thermal contact. These systems are in thermal equilibrium individually with another system B. If system B is in thermal equilibrium with system A, then both systems have the same temperature. Likewise, system B and system C have the same temperature. So the systems A and C will also have equal temperature. In this way, the systems A, B and C exist in thermal equilibrium state with each other. After learning to measure the physical quantities, temperature and heat, let us learn about the units used to express the measurement of these physical quantities. The SI unit of heat is joule, CGS unit is calorie, CAL. The amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius is called calorie. 1 calorie is equal to 4.186 joules. The SI unit of temperature is Kelvin, K. It is also expressed in degree Celsius, C. The degree Celsius is converted to Kelvin by adding 273 to the value of temperature in degree Celsius as per the relation. 0 degree Celsius is equal to 273 Kelvin. Temperature in Kelvin, K, is equal to 273 plus temperature in Celsius. Until now, we learned about temperature using larger bodies. Let us learn about temperature at molecular level through activities. The following table shows the differences between heat and temperature. Take two bowls, one filled with hot water and the other with cold water. Gently sprinkle some food color in both the bowls. Observe the motion of small grains of food color. We notice that the grains of food color exhibit jiggling movement, that is, they move randomly. This is the result of the random motion of the molecules of water in both the bowls. We also observe that the grains of food color have more jiggling movement in hot water than those in cold water. We know that every moving body has some kinetic energy, as the particles, that is, the grains of food color in both the bowls move with different speed, are said to have different kinetic energies. Finally, we can conclude that the molecules or particles of the hotter body have comparatively larger average kinetic energy than the colder body. In this way, the average kinetic energy of molecules of a body is indicated by the temperature of that body. In other words, the average kinetic energy of the molecules is directly proportional to the absolute temperature. Let us do another activity to learn more about the relationship between temperature and kinetic energy. Take a jar half filled with water and heat it to 60 degrees Celsius. Take a cylindrical glass jar which is transparent and fill half of it with hot water. Now pour some coconut oil over the surface of the water very gently, such that the water and oil do not mix. Close the jar with a lid containing two holes. Take two thermometers and insert them into the jar through the holes in the lid. Put the thermometers in such a way that bulb of one of the thermometer is inside the water and the other touches only the coconut oil. Now note the readings of both the thermometers. The mercury level in the thermometer kept in water falls, while the reading of the thermometer kept in oil increases. It is because the average kinetic energy of the molecules of oil increases, while the average kinetic energy of the molecules of water decreases. In other words, the temperature of oil increases while the temperature of water decreases. Some heat energy flows from water to oil. As a result, the kinetic energy of the water molecules drops and the kinetic energy of the oil molecules increases. In this way, water loses energy while oil gains energy due to the temperature difference between them. From the activities 2, 3 and 4, we learn the following differences about heat and temperature. Heat is the energy that flows and temperature is the quantity which decides the direction in which heat energy flows. After learning this, let us now learn how these quantities are associated with a system through the concept of specific heat. Let us perform the activity. To learn about specific heat, take a big jar, fill it with water and heat up to 100 degrees Celsius. Take two similar boiling test tubes with single-holed corks. Now fill one of them with 50 grams of water and another with 50 grams of oil. Insert two thermometers into the test tubes via the holes of the corks. Now fix them to a retort stand and set them in the hot water of jar. For every 3 minutes, observe the readings of thermometers. Note down the readings in your book. When the test tubes containing water and oil are kept in the water jar of same temperature for equal intervals of time, they both receive same amount of heat. Here, we find that the increase in temperature of the oil is faster than the increase in temperature of the water. The increase in temperature depends on the nature of the material. Let us perform another activity to learn more about the specific heat. Take 250 milliliters of water in a small beaker and 1 liter of water in a large beaker. Measure their initial temperatures using a thermometer and note them. These two initial temperatures must be equal. Now heat both beakers until the temperature of water raises to 60 degrees Celsius. Observe the heating time required to increase the temperature of water to 60 degrees Celsius in each beaker and note the readings. We observe that the time required to heat the large beaker is more than the time required to heat the smaller beaker. This implies that the required heat energy is more for water in larger beaker than water in smaller beaker for changing the same temperature. In other words, for same change in temperature, the amount of heat absorbed by a body is directly proportional to its mass m. Q directly proportional to m when delta T is constant. Consider it as equation 1. Now, take 1 liter of water in a beaker and heat it. For every 2 minutes, note down the temperature changes delta T. We will observe that the change in temperature increases with the time. This implies the change in temperature is proportional to amount of heat Q absorbed by it for the same mass m of water. Q directly proportional to delta T when m is constant. Consider it as equation 2. From equation 1 and 2, we get Q directly proportional to m delta T. We introduce the constant of proportionality S. Q is equal to Sm delta T. Here S is a constant for a given material. This constant is called specific heat of substance and is mathematically given as S is equal to Q by m delta T. Consider it as equation 3. It is defined as the amount of heat required to rise the temperature of unit mass of the material by a unit. The CGS unit of specific heat is calorie per gram, degrees Celsius, and the SI unit of specific heat is joule per kilogram. The units in different systems are interconvertible using the relation 1 calorie per gram degrees Celsius is equal to 1 kilocalorie per kilogram Kelvin is equal to 4.2 into 10 to the power 3 joule per kilogram Kelvin. We know that the rise in temperature depends on nature of the material. That is why the specific heat of the material depends on its nature. From the equation 3, we learn that the specific heat of the body and rise in temperature are inversely proportional to each other. However, every material exhibits some opposition to rise in temperature as its nature. Let us learn about the reasons behind this observation through the concept of internal energy. We know that the average kinetic energy of the molecules of the body is directly proportional to the absolute temperature of the body. The molecules or particles of the system, body or material contain different energies such as linear kinetic, rotational kinetic, vibrational energy and potential binding energy between them. The entire energy of the system, body or material is called internal energy of the system, body or material. When we supply heat to the system, body or material, it is shared in various forms. Such sharing varies from one material to another and with the temperature of the body. If the maximum share of heat energy is spent in increasing the body's linear kinetic energy, its temperature rises. For this reason, the specific heat is different for different materials. The equation Q is equal to ms delta T is used to find the amount of heat Q required to rise the temperature of a substance of mass m by delta T. Let us know about the applications of specific heat capacity. Applications of specific heat capacity. Water masses like oceans absorb large amount of sunlight, maintain relatively constant temperature. It is because of their high specific heat capacity. The oceans act as heat storehouses. They transfer the stored energy to the areas surrounding the poles to maintain moderate temperature between equator and the poles. The fruit watermelon contains large percentage of water. On removing from a refrigerator, it retains its coolness for a longer time than any other fruit. It is because water in this fruit requires sufficiently large amount of energy to rise its temperature by 1 degree centigrade. Samosas appear to be cool on the surface, but the curry inside it remains hot as the specific heat of its ingredients is high. Let us perform an activity for method of mixtures. Situation 1. Take 2 beakers of same size. Pour 200 milliliters of water in both of them. Now heat the water in both the beakers till they have the same temperature. Pour the water from these 2 beakers into a single larger beaker. Measure the temperature of water mixed in the larger beaker. Situation 2. Now heat the water in one beaker to 90 degrees Celsius and the other to 60 degrees Celsius. Pour the water into a large beaker from these beakers. Measure the temperature of mixed water in the larger beaker. Situation 3. Now, take 100 milliliters of water in one beaker and heat it to 90 degrees Celsius. Similarly, take 200 milliliters of water in another beaker and heat it for 60 degrees Celsius. Mix the water into a large beaker from these beakers. Measure the temperature of the mixed water in the larger beaker. Now, let us find the difference between these 3 situations. Assume that the initial temperatures of the samples of masses M1 and M2 be T1 and T2 respectively. Here T1 is the higher of the 2 temperatures. Let T be the final temperature of the mixture. The temperature of the mixture is higher than the colder sample's temperature and lower than the hotter sample's temperature. This implies that the cold sample has gained heat and hot sample has lost heat. The amount of heat lost by hot sample Q1 is m1s into T1 minus T. The amount of heat gained by the cold sample Q2 is m2s into T minus T2. As heat lost by the first sample is equal to the heat gained by the other sample from law of conservation of energy, Q1 is equal to Q2. Then it can be written as m1s into T1 minus T is equal to m2s into T minus T2. The above equation can be simplified as m1st1 minus m1st is equal to m2st minus m2st2. m2st plus m1st is equal to m1st1 plus m2st2. st into m2 plus m1 is equal to s into m1t1 plus m2t2. T is equal to m1t1 plus m2t2 by m1 plus m2. We observe that the temperatures of mixtures in situations 2 and 3 are not equal. Let us learn about the reasons for method of mixtures. Principle. When two or more bodies at different temperatures are brought into thermal contact, then net heat lost by the hot bodies is equal to net heat gained by the cold bodies until they attain thermal equilibrium. Net heat lost is equal to net heat gain. This is known as method of mixtures principle. For example, the heat loss from 100 grams of 80 degrees Celsius water is gained by 100 grams of 20 degrees Celsius water, resulting in a final temperature of 50 degrees Celsius. Let us do a lab activity for determination of specific heat of a solid. Click each tab to know more. The aim of this lab activity is to determine the specific heat of a given solid. Materials required are calorimeter, thermometer, stirrer, water, steam heater, wooden box, and lead shots. Let us follow the procedure. Determine the mass of the calorimeter along with stirrer. Note down the mass of the calorimeter. Now fill the water to 1/3 of the calorimeter. Measure the mass of the calorimeter along with water and note down the same. Place the calorimeter in the wooden box. Measure the temperature using thermometer. Take a few lead shots. Put them in steam heater or hot water. Heat them till the temperature reaches 100 degrees Celsius. Quickly transfer the lead shots into the calorimeter with minimum loss of heat. Observe that the mixture settles at certain temperature after some time. Now measure this temperature and also the mass of the calorimeter along with the contents, water and lead shots. Observations. Mass of the calorimeter and stirrer is equal to m1. Mass of the calorimeter, stirrer and water is equal to m2. Mass of the water, m, is equal to m2 minus m1. Temperature of the water in calorimeter is equal to T1. Temperature to which the lead shots are heated is equal to T2 is equal to 100 degrees Celsius. Temperature of the mixture is equal to T3. Mass of the mixture is equal to M3. Mass of the lead shots is equal to M3 minus M2. Specific heat of water is equal to SW. Specific heat of calorimeter is equal to SC. Inference. As the heat lost to the surroundings is zero, we can state that the heat lost by the solid, lead shots, is transferred to the calorimeter and water for obtaining final temperature. Let the specific heat of the calorimeter, lead shots, solid, and water be SC, SL, and SW respectively. According to the method of mixture, we know that heat lost by the solid is equal to heat gained by the calorimeter plus heat gained by the water. M3 minus M1 into SL into T2 minus T3 is equal to M1 SC into T3 minus T1 plus M2 minus M1 into SW into T3 minus T1. SL is equal to M1 SC plus M2 minus M1 into SW into T3 minus T1 by M3 minus M1 into T2 minus T3. Finally, we can calculate the specific heat of the solid, lead shots, using the above expression. Numerical problem. How much heat is needed to raise the temperature of 2 kg of copper from 20 degrees Celsius to 70 degrees Celsius? Hint, specific heat is equal to 3.9 into 10 square joules per kg degree Celsius. Click the tab to view the solution. Let us perform an activity for evaporation. Take a small amount of spirit in a cup. Pour a few drops on your palm. Your palm feels coldness. Let us see why this happens. Once again, take a few drops of spirit, say 1 ml, and pour the drops into 2 petri dishes individually. Generally, the petri dishes are shallow glass or plastic cylindrical lidded dishes used in the laboratory. Place both of the dishes under a ceiling fan. Close one of the dish with the lid. After 5 minutes, check the quantity of spirit in both dishes. We observe that spirit disappears in the dish, which is kept open under the ceiling fan. At the same time, some quantity of spirit can be found in the dish which is closed. Similar observations can be noted for the water drying up on the floor and in wet cloths under a ceiling fan. In all the above cases, the state of the liquid changes to vapor. This change in state of any liquid to vapor is called evaporation. Let us learn more about the process of evaporation to understand the reasons behind the above observations. The molecules of spirit continuously move with random speed in various directions when the spirit is kept in the closed dish. During their motion, these molecules collide with one another and transfer their energies. The molecules on the surface get enough energy to escape from the surface when they are collided with the molecules within the liquid. These molecules, after escaping from the liquid surface, collide with the air particles near the surface of the liquid. A few of them even return back to the liquid. Hence, when a liquid is exposed to air, the particles at the surface continuously escape from the surface until the entire liquid disappears. This process is called evaporation. Now, let us observe the reason for faster evaporation of spirit under the fan. In open air, the number of returning molecules is reduced to a large extent when air is blown over the surface of liquid. This is because any molecule escaping from the surface is taken away from the liquid surface, so this raises the rate of evaporation. That is why in an open pan the spirit evaporates quickly than when it is closed. In this way, we learn that the process of evaporation is a surface phenomenon. Temperature falls during evaporation, thus making it a cooling process. As the molecules of liquid escape from the surface into the air, the process of evaporation also involves phase change. The rate of evaporation of liquid is determined by the factor like temperature, surface area of the liquid, and amount of vapor present in the surrounding air. Example: when we work, the body produces heat. This increases the temperature of the skin. As a result, water present in the sweat glands begins to evaporate. Depending on the factors of evaporation, the body becomes cool. The reverse of evaporation is technically known as condensation. Let us learn about this process in detail. Take a glass tumbler. Place it on the table. Fill half of it with cold water. We know that the temperature of the cold water is lower than the temperature of the surrounding air. Air has water molecules in the form of vapor. Molecules of water in air with higher energy collide with the water molecules in the glass tumbler with lower energy. As a result, water molecules in air lose their kinetic energy. This causes a drop in the temperature, and molecules of water in air are converted into droplets continuously. Hence, the water molecule's temperature in the glass tumbler increases. This process is called condensation and is a warming process. Condensation can also be defined as the change from gas to liquid state occurring at the surface of the liquid. For example, when we complete our bath in a bathroom with hot water, the number of vapor molecules per unit volume is high when compared with the outside. When you dry yourself with a towel, the vapor molecules surrounding us condense on our skin, thus making us feel warm. Let us learn the reasons for this. Humidity. Some vapor is always present in air. This vapor may come from evaporation of water from the surface of rivers, lakes, ponds, and from the drying of wet clothes, sweat, and so on. Water vapor is the gaseous state of water and not visible. The presence of vapor in air is known as humidity. Similarly, the amount of water vapor present in the air is called the humidity of air. Dew and fog. In the early morning of winter season, we observe water droplets on the window panes, floors, grass, etc. The atmospheric temperature falls down during the winter nights. Hence, the surface of window panes, floor, grass, etc. become colder. As a result, the air surrounding them saturates and condensation begins. The water droplets condensed on such surface is known as dew. The entire atmosphere in that region has maximum amount of vapor when the temperature goes down. So the water molecules present in the vapor condense on the dust molecules in the air and form small water droplets. These droplets continuously float in the air and form a thick mist. The thick mist is called fog, which restricts visibility. Let us perform an activity for boiling. Take a beaker and pour some water in it. Place it on the burner with the help of tripod stand. Measure the temperature of water with the help of thermometer and note down the readings for every 2 minutes. Observe that the temperature of the water increases continuously till it reaches 100 degrees Celsius. After this, no additional increase of temperature is observed. While the supply of heat continues at this 100 degrees Celsius temperature, we can observe bubbles at the water surface. This state is called boiling of water. Let us learn more about the process of boiling. Process of boiling. There are several impurities dissolved in water, including some gases. The solubility of gases reduces when water or any liquid is heated. That is why bubbles of gas are formed in the liquid or water. In these bubbles, evaporation occurs from water molecules surrounding the liquid. The bubbles get filled with saturated vapor, whose pressure is directly proportional to the increase in temperature. At a specific point of temperature, the pressure of the saturated vapor inside the bubbles get equivalent to the pressure applied on the bubbles from the outside. So these bubbles increase quickly and collapse at the surface, releasing vapor present in bubbles into the air at the surface. When we supply heat continuously, the liquid is converted to vapor or gas. This process appears as boiling of water for us. Here the liquid phase changes to gaseous phase at constant temperature. That is why this temperature is called the boiling point of the liquid. In actual point, the process of boiling of a liquid is different from the process of evaporation. We know that the boiling occurs at a specific temperature where evaporation takes place at any temperature. The temperature remains constant at the boiling point until the liquid boils away. Latent heat of vaporization. Some amount of heat energy is used to convert the state of water from liquid to vapor or gas. This is called latent heat of vaporization. In other words, heat is required to change 1 gram of liquid to gas at constant temperature is called latent heat of vaporization. Assume a liquid of mass as m requires heat Q calories to convert its state phase of liquid to phase of gas. Then latent heat of vaporization is given by the expression Q by m and is denoted as L. SI unit and CGS unit of latent heat of vaporization is joule per kilogram and calorie per gram respectively. The boiling point of water at constant atmospheric pressure is 100 degrees Celsius or 373 Kelvin, and latent heat of vaporization of water is 540 calories per gram. Let us perform an activity for melting. Take a beaker filled with small ice cubes. Insert a thermometer into the cubes. Observe the thermometer reading. Now put the beaker with ice cubes on a burner with help of tripod stand and start heating the beaker. Then the ice cubes start melting. Observe the changes in the thermometer reading for every 1 minute until all the ice melts. We will observe that the thermometer reads below 0 degrees Celsius at the beginning and it continuously changes till it reaches 0 degrees Celsius. When the ice starts to melt, no change in temperature will be observed though heat is supplied continuously. The heat supplied to the ice increases the internal energy of the molecules of the ice. As a result, the bonds between the molecules H2O in the ice weaken and break. So the ice that is solid phase gets converted to water that is liquid phase. This complete process of conversion of solid into a liquid called melting occurs at a constant temperature of 0 degrees Celsius or 273 Kelvin, referred to as the melting point. During the melting process, temperature of ice does not change because the heat supplied to ice is utilized completely for breaking the bonds between the water molecules. Heat required to completely convert 1 gram of solid completely into liquid at a constant temperature is called latent heat of fusion. Consider a solid of mass m, which converts from the solid phase to liquid phase when heat Q is supplied to it. The heat required to convert 1 gram of solid into liquid is Q by m. Latent heat of fusion L is equal to Q by M. The value of latent heat of fusion of ice is 80 calories per gram. Freezing. We know that coconut oil, ghee, convert from liquid state to solid state during winter season. We also know that water kept in a refrigerator converts to solid ice. It implies that in the process of conversion from liquid state to solid state, the internal energy of the water decreases. Hence, the liquid state of water is converted into a solid state, ice of water. This process is called freezing. Technically, freezing is defined as the process in which the substance in liquid phase converts to solid phase by losing some energy from it. Freezing of water occurs at 0 degrees Celsius temperature and at 1 atmospheric pressure. Let us learn more about freezing through an activity. Take small glass bottle with a tight lid. Fill it with water fully without any gaps. Fix the lid strongly so that the water should not leak from it. Place the bottle into the deep freezer for a few hours. After few hours, take it out from the fridge. Observe the cracks appear on the glass bottle. We know that the volume of the bottle is equal to the volume of the water in the glass bottle. The bottle is broken when the water freezes to ice. This shows that the volume of the ice is higher than the volume of the water filled in bottle. In short, we say that water expands, increases in volume on freezing from 4 degrees Celsius to 0 degrees Celsius. This is enormous expansion of water. The density of ice is less than that of water, and this explains why ice floats on water. The image shown on screen gives a clear idea about the terms melting, evaporation, condensation, and freezing. Take up the following activities. Collect the information about working of geyser and prepare a report. Suggest an experiment to prove that rate of evaporation of liquids depend on their surface area and the vapor already present in the surrounding air. You have successfully completed the chapter E.